Let's look at this 2x5 zero-sum game between Rose and Colin. Rose has two strategies, A and B, and Colin has five strategies, A, B, C, D, and E, and the numbers in the cells are Rose payoffs. To solve this game, we can first start by graphing it, and we can draw two vertical lines, one representing Rose's A strategy and the other representing Rose's B strategy, and these lines can be marked with Rose payoffs. Now, Colin's strategies are just represented by slanted lines. So these slanted lines will indicate the Rose payoffs to each of Colin's strategies as a function of Rose's possibly mixed strategy. So if Colin plays A, Rose gets -2 if she plays A, and 3 if she plays B. If Colin plays B, Rose gets 5 if she plays A, and -3 if she plays B. If Colin plays C, Rose gets 1 if she plays A, and -1 if she plays B. If Colin plays D, Rose gets 0 if she plays A, and 3 if she plays B. If Colin plays E, Rose gets -4 if she plays A, and 8 if she plays B. So in equilibrium, Colin can anticipate Rose's mixed strategy and can therefore best respond. And that means that Colin can restrict Rose to a point on the lower envelope of Rose's strategy. No, Colin can restrict Rose to a point on the upper envelope of, no, Colin can restrict Rose to a point on the lower envelope of Colin's strategies. And Rose can adjust her strategies so she reaches the highest point on that lower envelope. Now, here we see against Rose's equilibrium strategy, which reaches the highest point on the lower envelope. Colin's only best responses are A and C. Therefore, we conclude that Colin plays only A and C in equilibrium, and we simplify the game down to this 2x2 game. Now, we then solve the 2x2 game. So if X is the probability that Rose plays A, then Colin must be indifferent between A and C in equilibrium, since this is a geometric property of what we've graphed here. And we can compute the payoff to Rose of Colin playing A. It is -2x plus 3y times 1 minus x, and the payoff to Colin is just the additive inverse of that, and the payoff to Rose if Colin plays C is 1x minus 1 minus x, and the payoff to Colin is just the additive inverse of that. And therefore, we can solve for x by setting these two Colin payoffs equal. We can now multiply both sides by -1, and then we can expand both sides. And then we can combine like terms. And then we can add 5x to both sides. And then we can add 1 to both sides. And then finally finish by dividing both sides by 7. And we verify that this is Rose's strategy. Rose just plays B with complementary probability. Now we can do a similar thing for Colin's strategy. So Rose must also be indifferent between A and B in equilibrium. So what does Rose get from playing A? Well, that depends on what Colin's mixing probability is. Let's let A be the probability Colin plays A. So then from A, Rose would get minus 2A plus 1 minus A, and Rose B would yield 3A minus 1, 1 minus A. And these must be equal. And we can solve first by expanding both sides. So this would expand to minus 1 plus A, combining like terms. Adding 3A to both sides. Adding 1 to both sides. And then dividing by 7. And now we can find the value of the game. The fact that Colin plays C with probability 5/7 follows from the fact that C is the only other strategy he plays in equilibrium. So what we could do is just calculate the payoff to Rose. If she plays A, we know it's the same as the payoff that she would get if she plays B. So it would be 2/7 from the chance that Colin plays A times minus 2 plus 5/7 times 1 from the chance that Colin plays C, which would be 1/7.